This video covers track plotting, which is the third part of visualization capabilities in Serpent. The features I'm presenting here are not very difficult to use. The syntax is simple, but there are a couple of things related to memory management that you need to know to be able to use these track plots. And to be specific, what I'm covering here is actually two features, track plots and track plot animations. So let's start with the standard track plotting capability. In order to produce track plots, you need to specify one or multiple geometry plots. And this involves using the plot or the new gplot input card, which I covered in the previous video. When you run Serpent with command line option tracks, followed by the number of particle tracks to be plotted, what you get is the geometry plots in which the particle tracks, starting from the source distribution, are drawn with these black lines. The names of the produced PNG files are appended with _trck to distinguish them from the standard geometry plots. The outcome is a bit different depending on whether you run the calculation in critical source simulation mode or external source simulation mode. So this example here is from a critical source simulation, in which case all the plotted tracks correspond to the first neutron generation. So the tracks are started from the initial source distribution and fission terminates the histories instead of producing the source particles for the next generation. The example here also demonstrates the effect of reflective boundary conditions, so you can see how the tracks are bouncing off the reflected outer boundary. For critical source simulations, the track plotter shows only the first generation of neutrons, but if you switch to external source simulation mode, what you get is the entire particle histories. So here's another example showing photon tracks in a spent fuel storage cask with radioactive decay source. The geometry comprises these 21 fuel assemblies inside the shielded canister, and the particle histories are started from the fuel rods from decay reactions. One use case for the track plot is to check that the source distribution that you get looks like it's supposed to. So you can do this by sampling a large number of tracks over the geometry. The problem, of course, is that if you do this, the entire geometry is then covered by these tracks, but if you apply time cutoff, you can limit the tracks to short segments. So in this case, the time limit is set to 10 picoseconds, so the photons can travel only a few millimeters in that time. And you can then see that the tracks will really start from these fuel rods. One note about the plotted tracks. So the geometry over which the tracks are plotted is a two-dimensional slice across the 3D geometry model. The tracks are projected on this plot plane, so you cannot really tell by looking at the tracks alone how much the particles move in the direction that is perpendicular to the plot plane. So it's therefore a good idea to produce multiple plots from different directions. Like in this case, this example here, you have an XZ plot of the previous spent fuel transport cask, also showing the movement of the particles in the axial direction. When you run a neutron external source simulation in a multiplying system, the population size can grow quite significantly even if the system is below criticality. This example here is an infinite cylinder made of fissile material with K effective around 0.97. So the source neutrons here are multiplied by a factor of 30 to 40 on average. And in cases like this, you will almost always get this error message on insufficient particle buffer size. The particle buffer is this data structure that is used to store neutrons produced in fission reactions during the simulation, and if the multiplication factor is high, the default buffer is easily overrun. The solution then is to increase the buffer size using this set nbuff input option. When I was preparing for this video, I realized that the way that the default buffer size is set is actually very inconvenient for producing these track plots, and you almost always have to increase the size to get them running. This issue will be fixed in the next update, but for now you just need to find a proper value by means of trial and error. So you can just keep increasing the value by a factor of 10 until the calculation runs. Now, if you have a supercritical system, the population size can begin to grow indefinitely, which means that there's no buffer size that can accommodate the new source particles. You can still run these supercritical systems, but you also need to apply some kind of a time cutoff additionally to limit the population growth. There's also another alternative to this, so you can use this generation cutoff with the set gcut input option, which limits the length of the neutron histories to the specified number of generations, regardless of how long the random walk takes in time. It's worth noting here that the generation cutoff should only be used with these track plots. So if you use it in a transport simulation where you are trying to produce some actual usable results, you will actually end up biasing your calculation, and the results will not be consistent with physical reality. It's also worth noting that you are simulating a random system, and with track plots the number of simulated particles is typically not that large, which further emphasizes the effects of this randomness. So depending on the branching of individual particle histories or even a single particle history, you can every now and then get this error on insufficient buffer size, even if some calculations are successfully completed. And in addition to neutron multiplying systems, you can also get a lot of branching and also these issues with insufficient buffer size when using variance reduction. This track plot here is for the previous spent fuel transport gas calculation with some additional weight windows based variance reduction technique applied, and you can see that the histories, they develop these multiple branches when they enter regions of higher importance at the outer parts of the geometry. Instead of plotting the tracks from beginning to end, it's also possible to produce a time sequence of images that can then be compiled into an animation. And you can do this with the set TPA input option. The input arguments define the starting and end time of the simulation and the number of frames. And each frame represents a snapshot of the particle population at that time instant. If the particles would be plotted as just as small dots over the geometry, it would not produce a very illustrative visualization of the behavior of the population. So to emphasize the sense of motion, the particles are actually drawn with these short tails. And the tail length is specified as one of the input parameters. Neutron tails are plotted in purple and photon tails in green. So if you have a coupled neutron photon transport simulation, you can distinguish the two particle types from each other. The last parameter in this set TPA input option is called the event bank size. This is another parameter related to memory management that you may need to adjust when producing these trackplot animations. The event bank is this data structure that is used for storing the collision points and other events during the particle random walk, which are needed for drawing the animated tracks. And if the event bank size is too small, you get another error message telling you that you should increase it. I have a couple of examples of trackplot animations here. The first case is the previous fuel assembly lattice calculation, but this time run in external source simulation mode. Since the system is well above criticality, I also set the time cutoff to 0.5 microseconds to limit the population growth. With trackplot animations, this cutoff is actually redundant because the end time is also specified by the set TPA input option. When I run the simulation, Serpent produces these 200 image frames, and I can use a graphics processing tool like this convert command line tool in the ImageMagick toolbox to combine these frames into an MPEG animation. This example here also highlights a fundamental issue with track plotting for these thermal systems. So the time scale here was set so to show the motion of fast neutrons. And this means that when the neutrons are thermalized and their velocity has dropped by several orders of magnitude, in this time scale they actually appear like they have been stopped completely. On the other hand, if I set the time scale suitable for thermal neutrons, like 50 microseconds, then you cannot really see the motion of the fast neutrons, and this because they are just too fast to be caught in multiple frames. And this is not really a flaw in the methodology, it's rather a limitation that's rooted to the physics. So the timescales of fast and thermal neutrons are simply so completely different that you cannot visualize them in a proper way at the same time. There is a way around this issue. So Serpent features this set SPD input parameter that allows you to override the speed of the simulated particles. So instead of moving at the speed that corresponds to the particle energy, all particles can be forced to move through the geometry at a constant speed. And this option only affects the internal clock of the particles without affecting the collision physics. So you can have the same physics simulation but in a time scale where you can simultaneously see the motion of both thermal and fast neutrons. The timescale issue doesn't concern photon transport simulations or even fast neutron systems. Like here's the previous infinite fissile cylinder example with increased fuel enrichment so that the system is above prompt criticality. And the animation here shows the exponentially growing neutron population. The final example here is the previous photon transport calculation for the spent fuel transport cask with variance reduction. You can see that you have a lot of splitting for photons that are trying to penetrate the thick radiation shield. And this is basically what variance reduction looks like in action. That's all I have for track plotting. If you have any questions, please let me know in the comments. And also note that there is now a description of this track plotting capability also in the new Serpent user guide. The topic for the next video is the STGR geometry type, which can be used for modeling the random distribution of fuel particles in high temperature gas cooled reactor fuels, but also for modeling the pebble distributions in pebble bed type reactors. This feature is pretty well known, but I've also seen some users avoiding it, possibly thinking that it comes with some added computational cost, which really isn't the case in reality. So I will be talking about the methodology behind the geometry type and also the performance compared to using regular lattice approximations. Thank you for watching.